So this is the last topic, and right there. So let's finish this. So we are building a metric space from a weighted graph, okay, and we need to prove the triangle inequality. The idea was suggested last time, so let's write it up. Okay. So proof. So somebody, how do we start? So the idea is good, but how do we start actually writing it? So let me refresh your memory. So this is the weighted graph. This is the where's the weighted graph? Okay. So each edge is assigned a number, but the metric is defined this way. Okay, so the distance that is derived from the weighted graph is supposed to be this, but is it a distance? We need to demonstrate that it is, and so and we just want to do the last one, the triangle inequality. Okay, so go. So, you know, you gotta get started, even though you might have no idea how you're gonna finish it. But you gotta know how what should be your first words that you're writing a proof like this. So what is it?
There's a D.
There's a what?
There's a D.
A D?
Distance.
So the D is defined. Okay, so this is already given. So we started with a weighted graph, then we define distance in that manner, or a number. We realize that it is indeed a number. Okay, now we need to demonstrate that this number D, which is assigned to every pair of vertices of the graph, it satisfies this property. So the proof should start the same. The property starts. The part that is actually missing from this property, because I'm writing just the form, only the inequality itself. But actually, it starts with saying, suppose A, B, C are vertices of the graph. Okay. So that's pretty much always works out the same. You start the same. You know what you're supposed to end up with, and but what you're supposed to end up with is never just an inequality or equation. There's a preamble, and the preamble is this. So and then you should in your proof have it reappearing. Okay. So if we want to say at the end something about arbitrary vertices of our graph, then that's how we should start. So we have A, B, C, and that way you have already narrowed down things that you're trying to say, and we're not talking about all the vertices at the same time. Suppose we kind of imagine that we picked arbitrarily 3 vertices from the graph, and then we're trying to do something about them. Okay? So, okay. Yeah. Okay. So yes. Not only it is a minimum distance, it is that's just to say that's just a number is not enough. You have to actually make a point that it is realized in a particular way. So it's not just that there is a number. It suffices just to say for a metric to exist, all you need to is a number. But in this particular case, we have to actually point out where it comes from. It comes from a particular sequence or path of edges from A to B. Okay, so let's try it. So pretty much we don't really have a choice but to take this definition and repeat it twice. Okay, so from A to B and B to C, and then try to also combine those two together so that we would have something similar for a path from A to C. Okay, so let me try that. So copy and paste, always a good thing. Okay, so I'm gonna paste it twice. Okay, well, um, something didn't work out. Well, it didn't work out the way it's supposed to. It looks different for some reason. Okay, anyway, so this just move, oops, N. Okay, okay, oh, no, N it goes at the top. Okay, let's go away. Okay, so we are doing summation N from K from 1 to N. And however, here it is the minimum is over all paths. Okay, so that's the definition. That's the definition. But because it is our graph is finite, then it's not a minimization in the sense as you see in calculus, which may or may not be attained, but rather it is always attained. There is actually a path. Then there is a path. There is exactly a path that gives us DAB. Okay, so in other words, rather than try to minimize it, let's just say DAB is equal to sum k from 1 to n omega xk plus 1. So that is a particular, this is W, particular path. So path is x a is equal to x naught, or do I start with 1? I start with 1. Then x2, x3, xn, which is b. Okay, so that is our conclusion that we want to use, that we derive it directly from the definition. So we pick the one that will be less than or equal to every other path, and but we pick the specific one. Okay, then what we do is we take that and repeat it one more time for the other pair. So we did this pair, now we're doing that pair. Okay, so let me try to do that again in a similar, by copy and paste. Okay, so there is a path that gives us BC. Okay, I erase this and I'll have BC. Okay, so BC, same formula. This is B, this is C. Okay, we probably will have to rename the vertices as well. So how about we call them Y's rather than X's? Y, 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 and Y, Y. Okay, so I'm trying to, as you can see, I have the picture at the top. I'm referring to it, but indirectly and implicitly. So I'm trying to write up the proof that is independent of the picture. Okay, it's just for reference, for convenience. So as you can see, we have then two paths, one from X to Y, from A to B, the other one from B to C. Okay, then the next step is what? There is one more thing, just to be careful, we want M here.
One more path, right?
Yes. So what do we do next?
I'll repeat that again. A to C.
Yeah, we'll probably, let's see, is it really a wise direction to take? So that what you suggested is reflected in the picture. So we have indeed three paths, okay? But so do I need this? I would suggest instead. Combine these two. We already have a path from A to C. This is. Yeah, combine these two together. It will give me a path, right?
That's the minimum.
And then, well, it might not be the minimum. We don't know that. But it is a path. So it will be at least as long or longer than the minimum. Okay, so form a path from A to C from these two. So you can be very specific. So A is equal to x1, then it is x2 on. Xn is equal to B, which is also equal to y1. And then you go on y2, y3, on, and you have ym, which is C. Right? It is a path from A to C. It has n plus m edges. No, it has n plus m minus 1 vertices, I believe. Okay. Okay, so then what we need to know about it is its length. Then the summation along this curve, which we're not saying is the distance, but we do say that the distance from A to C will be the distance of A to C is the minimum of all paths. This is just one path, so this will be less than or equal to the sum of the weights along that path, along that special path that we picked. Omega xk plus 1 plus, I keep saying omega, it is a w, yk plus 1. So here I run k from 1 to n, k from 1 to m. So it is a path from A to C, and which means that its total weight should be larger than or equal to the distance between A and C, because DAC is a minimum of over all of these paths, all the total weights over all these paths, and we know that this is DAB, just what we were reading above. This is DAB and this is DBC. Okay. So, any questions about it? Well, there's another one. It's kind of a profound way to look at it, to this proof, is, well, here it is. An interesting way to look at it is, hold on. Well, if they were oriented, then that would be, we would have more interesting algebra going on if our paths were oriented. In other words, from A to B is not the same from B to A. But this one is just a metric space, so it is just measuring distances, and that is the best we can do. But it is interesting that on that picture that indeed they may have nothing to do with each other. And the two shortest distances combined together will not necessarily produce the shortest distance altogether. This is pretty much in every metric space is the case, because it's That's why we need the triangle inequality to begin with. Okay, so the graphs, once again, Y graphs might be important. The example that I thought of just recently came up is genetic analysis, or what's called the, you send your saliva to some place, and they do genetic analysis of you take your genes. They are, in fact, they tell you your background, ethnic or otherwise background. And so how does it work exactly is really hard to tell, but the general description is there, and that is they pretty much break the DNA into smaller pieces. Okay, and then now this is crucial. They match up your DNA with other people's DNA by comparing those pieces, if they coincide or they're equal. Or they may contain similar pieces inside of them. Okay, so and then based on that, they will tell you whether or not you're close to a particular person, and they can actually predict, not statistically, whether or not this person, for example, your third cousin, and you may, if you do it, you might get a bunch of third cousins from all over the world. So they cannot really trace ancestry, where you came from, but rather nothing they look nothing but those strings of DNA, and then you can imagine that that's how they would be tracing people. So they would literally compare. That's what's still to think of. How do you compare two strings of say numbers? How do you compare and tell whether or not they're to what degree they're similar to each other? But once that's established, then they have many strings. How many strings, for example, you share with another person will indicate how close you are. Okay, so not how far you are, but how close you are. So you gotta take something like the reciprocal, but then the point is then you can from A to B and to C. You will be adding these distances in order to actually compare, have a whole population compared to each other, and sort of you will have a graph with dots, non-nodes are the people, and the edges are whether or not they share any DNA, with weights indicating how similar those strings of DNA are. Okay, and that way they predict the similarity in the background, and so if they know where the person came from and you are similar to that person, they will predict that your background is also similar. Okay, so that's how one of the applications of metric spaces of graphs that you can think of. Okay. Okay, so that is metric spaces on graphs. So this counts as technically as discrete mathematics, I suppose. So we have had algebra, we had number theory, congruences, all the divisibility and so on. We had modern algebra group theory, okay, and now some graphs, so it's discrete mathematics, and but we're really aiming for metric spaces of spaces of like Euclidean and non-Euclidean geometry. So this is a more extreme case of metric space. So which of these more important? If you think about it, if you are taking linear algebra, then your next course will be modern algebra probably. So that is a good. So then you'll be studying groups anyway. So that's a step in the right direction. If you haven't taken linear algebra, then groups will. If you understand groups, it'll be easier for you to understand vector spaces, which is what linear algebra is about. Okay. So that's all good, but really for better or for worse, calculus is considered very central to the mathematics curriculum, and so which means that everything related to calculus probably will come first, and that is why these metric spaces are important, because you want to try to build a theory of calculus on a more solid foundation, and specifically so in such a way that, for example, you don't have to worry about dimensions ahead of time, and so you have an equal treatment of you don't have to make that transition anymore from calculus 1 to 3, where you have one dimension, you have 3 dimensions or more. It's the same thing. Okay, so that's what we're trying to establish here, and so that's the next topic is then would be what sequences in metric spaces. So technically it's not calculus, technically it's topology, but it is a part of a calculus curriculum because everything about sequences, convergence, limits, continuity, it's all topology, but it's part of calculus traditionally. Okay, so we continue doing topology, moving in that direction. So from that just geometry and measuring distances, we're moving to sequences in metric spaces and their limits. Okay, so they are much easier than dealing with limits of functions. Okay, so let's just recall what we know about R and the sequences in R. So that's my metric space is R. So you have Xn converges to A if. So let me repeat that definition again. For any epsilon greater than 0, there is an n greater than 0 such that for all n larger than n capital, xn minus a is less than epsilon. Okay, remember this definition from calculus 2. Okay, so the picture usually you usually visualize something like that by having your x-axis here, and then you have a sequence x1, x2, and starts to accumulate, and then on and on. The step is small, and somewhere you put here and you call it a. Okay, so that's what it means for xn to converge to a. So that is how it is treated in calculus. Now we could actually, I already pointed out what we would do with this in order to get rid of numbers to begin with as much as possible. Even though epsilon these will remain numbers obviously, but now convergence will be happening not on the x-axis but in some abstract metric space. Okay, so then if we look carefully at this expression over here, we can see once again, or maybe you just remember what this is. What's the meaning? Xn minus a absolute value in R. It is the distance from or between xn and a. Okay, so then in that is the idea where you know what the distance is in general in the metric space. So well, just replace it. Just go straight ahead and replace this expression with the distance. So I just write it out: x or xd, a metric space, xn converges to a, and then everything is repeated except for the very last part. So once again, just to make that point, I will do copy and paste. So though I can write fast enough, but it is just to make that point, I will paste. Okay, so it's exactly the same thing. Okay, so I will just replace the bottom where whatever is circled. I will put what we said this is, and we said that this is. So let me write it out. The distance, well, you don't also have to say we have a formula for it, right? So we have a notation, so that probably will be easier. So I'll just put d, x, and a. Okay, the end. So that's the work is done. The distance is getting smaller as n grows. Okay, so the payoff is right away is pretty good because you just go with we jump straight to R2, still Euclidean space, and what we're talking about there is some point A here, and we are talking about a sequence that converges. What does it mean? It means that the distance from that point to xn is getting smaller. So if this is x1, x2, x3, x4. As you can see, this is not real anymore, but you are measuring the distance from xn to A, and then you have a convergence. Okay, so in fact, you probably can't even simplify this further, and you just say dxn A converges to 0. Okay, so that is the most convenient way of handling convergence in n-dimensional space or any metric space as well. You just say that the distance between xn and A converges to 0. In what sense? In the sense of numbers, because the x might be of any nature. Okay, so metric space, the nature of the elements or points is unspecified. The distance might come from all directions. However, the distance will be a number all the time. So we'll just ask that distance to converge. That distance, this is a sequence of numbers, right? dnx is a sequence, but not of elements of x. It is a sequence of numbers. Okay, so it converges to 0, just like that picture indicates, right? So this is not the point. So this is still x. This is my x. This is my x. Okay, but we are ignoring that. We concentrate on only one aspect of the sequence, and that is the distance to A. And if that sequence of numbers converges to 0, then you have convergence xn to A. So this is, if I set these side by side like this. So that's one. That is the interpretation of what? Of this. Like so. Like this. That is the interpretation that metric spaces allows us to make. Convergence of points points in the metric space is interpreted in terms of convergence of distances. The end. Okay. So before we proceed with this, well, maybe let's do something theoretic and abstract. And that is just make sense of this definition, right? So after all, so let me state the definition. So suppose XD is a metric space. Okay. Well, what is a sequence? I hope. What is a sequence? In a set theoretical way, how do we interpret a sequence? I just want to make sure that we understand what that is. What is a sequence? So sequence in X. So x1, x2, xn. So what is it? Is it a set? What is a sequence? It is a sequence of points. That's what I'm trying to say. So each of these belongs to X. Yes, but is a sequence a subset of X? It looks like a subset, right? But is that it? So this certainly looks like a subset, yes. The notation we use for it is x sub n in braces, okay? But the order matters. Well, it is not just a subset, there is more to it, because the order matters. So if you cannot just rearrange. A set has no structure, so it's a bag of points. Okay, you can shake it, and it's the same set. If you that whatever you have in the bag, you can shake it. It will be the same content. About the order of the elements of a sequence matters. You can also have repetitions, right? And it's still a sequence. You can have a constant sequence. If you take a constant sequence, it will have only one element, right? But it's not the same. It doesn't mean that it is a point. It is, what is a sequence? Well, if it is not a set, it is not a subset, the standard answer we have, what is it? In this set, what?
Anti-set?
No. The standard answer that we have. In set theory, everything is either a set or a subset, or it is...
A null set?
No.
Okay.
What's the next? You study sets, and then what do you study?
Groups?
No. No, this is just sets. There is no extra structure. So it's still set theory. Suppose we have a set. We study sets. And then what do we start studying? How do we relate sets to sets? Functions. So sets, then you study functions that relate sets to sets. This is a function. Okay? What is that function? What's the range? What's the domain? What's the domain in range? Oops, what did I do? It's a function, so what is the function? What's the input, what's the output?
Would the domain be x1 to xn?
No. 1 through n. Remember when you plot in calculus 2, you plot your sequences. You put n here, and this is what the sequence looks like. 1, 2, 3, 4. These are the input values, and these are the output values, which may or may not be on the x-axis, whatever you call that x-axis or not, but those are the output. So it's a function. Say if you want to call it f, it will be from say 1, 2, 3 to x. Everything is either a set or it is a function on sets in set theory. Then you might proceed on from set theory to things such as group theory. Then you add extra structure on top of a set, and with some special functions. Or you do metric spaces. Once again, you add some extra structure to it. But that's all there is. It is a sequence. That's what the sequence is. It starts at 1. It could start also just as well, just as good. A sequence that starts at 2, starts at 3. They're still sequences. But once again, that's what guarantees that there is order that matters. The order of elements. It's a interpretation that makes it unambiguous of what a sequence is. It's not its values. Remember, the function has it is correspondence between input and outputs. Just taking all the outputs together as a set is not enough to capture what the function is. Okay, so because, well, you don't know what the domain is. Okay, so then f of n is xn. So that's the interpretation that certainly important for calculus. So sequences are functions. It just happens to be simpler than functions that you study in calculus early on, because those are defined on, say, intervals, and they have a whole continuum, an interval of values of inputs, and this one has only countably many inputs. Okay, so that's the typical situation. Countably many inputs. Okay, so that is why sometimes you actually start studying calculus with sequences, not with functions. Even though your interest is really functions, but sequences are also functions, but simpler ones. Okay, so they are much easier to study. So limits are simpler, algebra is simpler, everything is simpler. And you can think of them also like for interpretation could be like dynamics, you jumping from point to point to point to point. So that's another way to think about sequences. Rather than functions, a good interpretation of a function is something that depends on time. So some quantity depends on time and it varies. Okay, but this is even simpler because you jump from one location to the next arbitrarily. Anyway, so that's what a sequence, or what sequence is. And now finally we say that A is the limit of xn if we know what that is, dxn A converges to 0 as n goes to infinity. Okay? So this is still in a metric space. The limit, and we also say xn converges to A. That's the language that we use. Okay, so so with the second part of the definition, what do we need to examine? With definitions, we usually have some issues to address. Look carefully at the definition, or you might recall what you remember from Calculus 1 or Calculus 2. What issues do we have to address when we have defined a limit? Remember early in this course, every time you define something indirectly, you don't say what A is, we say that A satisfies a certain property. That's a certain property that A is supposed to satisfy. So then what can happen?
A cannot satisfy that property.
It can what?
Cannot satisfy that property, making the statement false.
Yes, certainly. Any given A might not satisfy that property. A might not satisfy that property. So any given A might not satisfy this property. So in that sense, you are sort of testing that number. I'm sorry, A is not a number. A belongs to X. Okay? So that A in X might not satisfy this property, which means that it is Xn does not converge to A. However, if you remember calculus, that certainly is not a problem. In fact, we do know that it does not have to. A sequence does not have to have a limit. So we don't really have to go all the way back and pay too much attention to it. But we certainly know sequences that diverge. So, in fact, not any given A might not satisfy the property. There might be no such A. There may be no such A in X. So, in other words, you take every A in X, verify this property, and it fails every time. So, sounds complicated, but really if you go back to Calculus 2, you should be able to easily think of examples when this is the case. Okay, so give me an example of divergent sequence from Calculus 2. Real numbers, so not to worry. Divergent sequences. n squared, why not? Xn is equal to n squared, or it could be n, or it could be, this is a good example, negative 1 over n. So these two go to infinity, this one does not. So these are all diverge. So I'm not going to go back into this. So that will be your homework. Prove that indeed these sequences diverge. Okay, and then so that, because this is calculus 2, so I don't want to spend too much time on it. But there is the second issue, which also certainly comes up in calculus 2, but this time it's more subtle, and that is what else can happen? So there might be no such a, so there is no limit. That's what we have discovered here. There is no limit. What else can happen? The issues always follow two issues that follow every definition that is indirect, or such a thing might not exist. And the second one, it does exist, but. What can happen? Okay, so I'm doing something that I already did some time ago. Point out the grammar. So there might be more than one, right? Just as with everything else, there might be more than one. So is it possible to have two distinct limits for the same sequence? What's the answer? If you know from calculus 2, is it possible to have two distinct limits for the same sequence? No, that's not no. I mean the definition. So they're the one side that they're more exotic types of limits of functions, and you can approach a or their value from the left, from the right. That's not it. There is no ambiguity about this definition. N goes to infinity. Distances go to 0. We still speak of real numbers here. Calculus 2. Sequence. Can a sequence have two distinct limits? What? No. So that's why I'm using the, and I skipped over that extra analysis that we were supposed to conduct. And you, instead of using the limit, you should have been using the A is a limit if it satisfies this property. So any number A that satisfies this property is called a limit. Okay, then you carry out that analysis that we're just starting on, and then you conclude, well, actually there can be only one. There might be none. That's the previous example, but if there is one, there is no other that is also satisfy the same property. Okay, so that's what we are want to address, not based on the examples, not based. This is certainly a conclusive answer for calculus 1, but now I want to answer the same question with the same answer for all metric spaces. Okay, so no matter how exotic your space is, there can be only one. There can be only one limit. Okay, so we will derive it from nothing but what the three axioms of the metric space and this little definition over here. Okay, so in fact the idea is really uncomplicated if you think about it. Is it, if you deal with numbers, just to refresh your memory? So once again, if these are my n's, okay. So and these are my x's. Okay, is it possible for two different values to be like centers of accumulation of the values of the sequence? So they have to be they have to stay within a certain distance from these two lines, either like this. Okay, that's a convergence for you, or like this, not or like that. So here xn converges to A, and this is xn converges to B. Okay, so as you can see, it's getting closer and closer to that horizontal line, and it will in fact stay within a certain strip. Okay, like this. A certain strip around that line supposed to contain all the elements of the sequence up to a certain below a certain distance, below a certain n. So if we go back to the definition here, the original definition of convergence among numbers, that definition over there. So that picture that I made there is certainly acceptable. But if you actually wanna look at the function, then this is what you see is this. So this is my x, and I'm talking about these little distances, little intervals around inside of which all the sequence will have to eventually end up. It cannot, however, end up in the two simultaneously. So I cannot take these two sequences, combine them into one, and then claim that they both converge to these two numbers separately. So that's all good, but we want to prove it in the abstract, based on nothing but the axioms. Okay, so we'll do it